In this lecture, I will discuss rotational motion and the different physical quantities that are used to describe rotational motion. We will see that there is somewhat similarity between linear quantities for motion, such as velocity, speed, acceleration, displacement, and the quantities that are used to describe rotational motion. The first quantity needed to describe rotational motion is the angular displacement. The angular displacement theta is the angle through which a rotating object turns during rotation. So consider this disk, and this is a top view. This disk is going to rotate in counterclockwise direction, and let's take a point P on the edge of the disk. So the point P initially will be at some initial position, and then as the disk rotates, that point P will get to another position which we'll call final position. So then the angle that is subtended between the two positions of the point is the angle theta right here, or in other words, that's the angular displacement. And so simply when an object rotates, the angle that it rotates through is called the angular displacement. The units for angular displacement are called radians in the metric system. In the imperial system, we have revolutions, and also we have degrees, which do not belong to any measurement system. So those are the three units that are used to measure angles. And of course, those would be the units for angular displacement. Let's see what is the relationship between the three units. This would be useful information for creating converging factors when angles or other quantities that involve rotation require convergence of the angular unit from one kind to another kind. Okay, so one revolution is equal to 360 degrees, which is equal to 2 times pi radians, where 2 times pi must be calculated as a number to get the actual angular value for the angular displacement. So one more time, one full revolution is equal to 360 degrees, or 2 times pi radians. The next quantity that is important to describe rotational motion is angular velocity, and of course its magnitude, which is known as angular speed. Angular velocity is a vector quantity which is defined as the ratio of the angular displacement theta, which is the angle of rotation, and the time of rotation t. So the angular velocity omega is the ratio of angular displacement or in other words, the angle of rotation and elapsed time. In a formula form, this relationship looks like omega is equal to the angular displacement theta divided by the elapsed time t. The units that can be assigned to the angular velocity based on the units of the angular displacement in the units for time would be radians per second, which is the metric unit, revolutions per second, or revolutions per minute, which is the imperial unit, and degrees per minute is not a common unit, so we are not going to list it here. Since the angular velocity is a vector quantity, that means that it has direction. Now, the way to determine the direction of the angular velocity is by using the right-hand rule. So let's describe the right-hand rule. The right-hand rule states that if you wrap the fingers of your right hand in the direction of rotation, the thumb of your right hand will then point in the direction of the angular velocity vector. Let's see what that means. So imagine this is your rotating disc, and it rotates in counterclockwise direction. The axis of rotation is straight through the center of the disc. Now, if you wrap the fingers of your right hand in the direction of rotation, that means like so. The thumb of your right hand will point in the direction of the angular velocity vector, which is up. And so this is the angular velocity vector. What happens if the disk was rotating in the opposite direction, in clockwise direction? So the disk rotates like so. The axis of rotation again passes through the center of the disk. In this case, using the right-hand rule, if you orient the fingers of your right hand in the direction of rotation, so like so, then the thumb of your right hand will point in the direction of the angular velocity vector, which will be this way, down that axis. So the angular velocity vector in this example will be directed down. This is a very straightforward and simple rule that can be used to determine the direction of the angular velocity vector. Notice that the angular velocity vector here points in a way that is completely different than the linear velocity vector for a rotating object. So just as a reminder, I'm going to sketch that right here at the bottom. So we have a small mass that rotates in a circular trajectory, and we discussed the velocity of this small mass, and we said that it's always tangential or tangent to the trajectory. So the velocity and the trajectory are both in the same plane. Here, in the situation of rotational motion of a solid object like this disk, the angular velocity is it's perpendicular to the plane in which the object rotates. So conceptually, this is a very different situation. But the right-hand rule, as shown for those two examples, helps identify the direction of the angular velocity. Another important quantity for description of rotational motion is the angular acceleration. To explain the concept of angular acceleration, let's consider, again, a disk that rotates, and this is a top view. The rotation happens about an axis that passes straight through the center of the disk, and let's say the disk rotates in counterclockwise direction. So then, again, let's consider a point from the edge of the disk. Let's call that point P. And so the point initially has angular velocity omega initial, and so this is at initial position. So as the disk rotates, point P gets to somewhere else on the edge, a different position, final position. And now the angular velocity is different. The angular velocity is different. Let's call it omega f. So let's say that the disk was speeding up as it was rotating. Then I can calculate the angular acceleration as the difference between the two values of the angular velocity, omega final minus omega initial, divided by the time for point P to get from initial position to the final position. In other words, the angular acceleration is equal to the ratio of the change in angular velocity and elapsed time. Angular acceleration is denoted with alpha, and this is equal to omega final minus omega initial divided by the time t. The units which the acceleration gets would be, in the metric system, radians per second squared, and in the imperial system, revolutions per second squared. So I defined the three important physical quantities necessary to describe the motion of a rotating object. Those three quantities were angular displacement, or angle of rotation, angular velocity, and angular acceleration. Let's do a few examples to show how these three quantities are used to calculate problems involving rotational motion. Let's find the angular displacement of a rotating disk which turns at 50 radians per second over 7 seconds. So what we know here is the angular velocity, which is 50 radians per second, and we know the time of rotation, which is 7 seconds. What we want to find is the angular displacement theta for the disk. Well, we know that there is a relationship between the angular velocity, angular displacement, and time of rotation, and that relationship was that the angular velocity is equal to the angular displacement divided by the time of rotation. So from here, the angular displacement is simply omega times t. And now if I plug in the values that I know, that's 50 radians per second times 7 seconds. That is equal to, well, the time units cancel out, that is equal to 350 radians. Now let's convert this into revolutions. So to convert to revolutions, remember that one revolution has 2 times pi radians. So 350 radians I will multiply by 1 revolution and divide by 2 times pi radians. The units for radians cancel out, and so this becomes 350 divided by 2 pi, and the new units will be revolutions, and this is equal to 55.7 revolutions. Let's also convert that into degrees. So we know that 360 degrees, which is 1 full revolution, is equal to 2 pi radians. So we have 350 radians times 360 degrees divided by 2 times pi radians. The radians units cancel out, and so what we're left with is 350 times 360 degrees divided by 2 pi, which is equal to, it's equal to 20,054 degrees. Let's do the following example. A CD is rotating counterclockwise while speeding up from 5 radians per second to 23 radians per second in 2 seconds. What is the angular acceleration of the CD and what is the direction of the angular velocity vector? So, let's see what information we know. We know the initial and final angular velocities. So omega initial is 5 radians per second and omega final is 23 radians per second. The time of rotation for which this change happened, t is equal to 2 seconds. We are looking for the angular acceleration and also the direction of the angular velocity vector. So for the acceleration, we know by definition that is equal to the difference between the final and initial angular velocities divided by the time of rotation. That means that's 23 radians per second minus 5 radians per second divided by 2 seconds, which gives 18 radians per second divided by 2 seconds. So this is 9 radians per second squared. That is the angular acceleration of the CD. Now let's look at the second part of the question. What is the direction of the angular velocity vector? So for that, I'm going to use the right-hand rule. The right-hand rule was the following. For a rotating object, place the fingers of your right hand in the direction of rotation, and then the thumb of your right hand will point in the direction of the angular velocity vector. So let's make a sketch of this CD. This CD is simply a disk that rotates counterclockwise, and the axis of rotation will be passing straight through the center of the CD. So wrapping the fingers of my right hand in the direction of rotation leaves my thumb to point up like so, and that is the direction of the angular velocity vector. With this, I'm concluding the part of the lecture that describes the quantities that are necessary to describe the rotational motion of an object. In the next part, I'm going to describe quantities that are used to define how the rotational motion of an object changes, such as acceleration or deceleration during rotation.